Log on, tune in, find out. Another good idea from Cambridge.
Welcome our next speaker. It's Nicholas Witte, Melbourne, and he's going to speak about Askey-Wilson polynomials.
Thanks, Ta. Yeah, I'd like to thank the organisers for the invitation and also the accommodation of my late request. And so thanks, Peter. So it's good to be here. So unfortunately, the word deformation has been used in several different instances in this meeting. So I should warn you that it means something quasi-isomonodromic, okay, in this particular case. Okay, so quickly the outline. I want to suggest an idea which is possibly not very original or new, and I believe a fruitful idea that there's some correspondence between the Sacco scheme of all of the Painlevé equations and the Askey table of hypergeometric orthogonal polynomial systems. And then I want to introduce some ideas which are not completely novel at all, but they're probably not so well known. And so the first idea is the classification of non-uniform lattices or discrete lattices that will apply here. And they have associated calculus with those, and to briefly describe that. And then I want to set up systems of orthogonal polynomials and associated functions on such non-uniform lattices. And also introduce the notion of a semi-classical weight appropriate to those lattices. And that really is the core defining characteristic of this work. And then I'll construct the first member of a lax pair. It'll be a divided difference equation in the spectral variable. This is work that's not new. It was initiated in a pioneering work by Alphonse Magnus. But I want to continue beyond that, and I want to actually introduce the notion of a deformation of such weights, and respecting that kind of structure I've already introduced. And then one can find a second member of a lax pair associated with that deformation. And then the problem starts to look rather familiar. From this point on, we look at the compatibility between those two structures, and we attempt to look at evolution equations. Now, what I'm going to do is give a first part which outlines the general theory for an arbitrary lattice, okay? But I want to be very explicit and very specific, so I'm going to choose an example, and I'm going to take the Askey-Wilson system as my example, okay? And try to make it very concrete. Okay. Right, so this is something I'm sure virtually everyone here is familiar with. So just to give some background, from the random matrix point of view, the particular weights here, the particular Painlevé systems that arise here, say in Painlevé 4, 5, and 6, arise from weights from the Hermite and the Laguerre and the Jacobi weights in a very natural way. Well, basically what I'm going to tell you is the continuation of such a program of activity into the discrete setting. And okay, so I wish I could show these simultaneously, but okay, so here's the Askey table. As I mentioned earlier, these particular cases here and here, and rather natural deformations, form the basis of a lot of important work in the random matrix context. And so basically it's with that kind of a motivation that this talk should be seen. Now, I just mentioned earlier on in the program there was some work from a colleague in Melbourne, Chris Omerod, and he would have talked about a realization of this program in regard to the little q Jacobi weight. So in fact, what you can show is that you can deform that weight and actually show that the evolution system in that new deformation variable is actually the D5 Q-Panleve system, and that was also shown by Bjarne in a slightly varied context as well. Okay, so as I mentioned, I'm going to concentrate on this particular example because amongst this table there are what I would consider regular cases or generic cases. So this is certainly one of those examples. Okay, so the particular operators that we've seen so far have been in these two classes. That is what I would call a linear lattice and the Q-linear lattice. So this is a lattice where the successive x-coordinates generated, as you can see, in this picture by two parallel lines. And so this leads to an arithmetic progression in these particular coordinates. And it also leads in a canonical sense to the forward difference operator as the appropriate divided difference operator here. And the other set of difference operators that have been appearing here are the Q operators. So they're the ones that are appropriate to this Q-linear lattice, where the successive lattice points are generated by the successive y-intercepts by these two intersecting lines here. And of course Q is related to the ratio of the slopes there. But such a classification is not the full story. And in fact, it's eloquently explained by Magnus in 1988 and is fairly common knowledge in the orthogonal polynomial community, and certainly in the Russian school, that the particular cases that I gave you earlier, in fact, an example of this construction. So what you want to do is find a divided difference operator of this structure, where the two sample points, y plus and y minus, are the points that you sample, the particular function you're applying here, and you divide by the difference of the coordinates. And the simple fact that you want to have the situation where such a functional dependence then means that any polynomial of exact degree n gets mapped to one of degree n minus 1 means that the y plus or minus, that is the advanced and the retarded nodes, are given by the two y roots of a quadratic equation. Okay, and you can classify those in regard to these two quantities in terms of the discriminant and in terms of the theta here. And just to point out, I'm going to define an integral on this lattice with support G in this particular way by a Riemann sum. So just quickly to go to the classification aspect in terms of these two parameters. So the two linear cases that we have earlier are the cases where the theta parameter vanishes, but you get the conic sections for the other cases. So where that parameter is non-zero, then you get these classical conic cases, and the appropriate operators I have given here in this particular case. So I'm going to be concentrating on this lattice, which is in a sense a master lattice, because if you if you reverse the symmetrization process, then you can recover the other lattices from either of these by limits. Okay, so here's an example of the quadratic lattices. So you have the quadratic lattice and the Q quadratic lattice in the elliptic case. So you notice here the successive coordinates on the lattice, x1, x2, x3, and so forth, are kind of distributed in this way. And the interesting fact that arises here is that if the modulus of Q is not a rational multiple of pi, then you eventually densely fill an interval which runs from here to here. And that's the case with the Askey-Wilson system, which is defined on minus 1, 1. So even though you have you don't need to have a finite discrete a lattice system necessarily with these operators applying. So in the canonical Q quadratic lattice system, so there are some conventions I'll set up here. Z you should think of as being a phase on the unit circle, x being its projection on the -1,1 interval. X will be my spectral variable in my applications. There is a parametrization of this particular form in terms of S as an integer and in terms of the advanced and retarded points. So this is a specific definition of the Askey-Wilson operator. So it's sampling the function where the projected coordinate is from an advanced phase and subtracting the case where it is the projected coordinates comes from a retarded phase. And you also need a mean operator to go along with this divided difference operator as well. And just a point to note is that the characterization is essentially given by the fact that the sum of these two nodes is a linear function of x, and that the difference squared is a quadratic function of x. So for this preliminary part on the general theory, I'm not going to assume any particular lattice. I'm going to be able to treat every lattice, and in fact, there's no advantage in treating a specific lattice. It's quite elegant and quite simple, just to use a generic lattice in a quadratic system. Okay. Right. So there are, as opposed to the monomial basis and the kind of differential situation, it is often useful to use an adapted basis for these lattices, and you can find another set of kind of bases according to this criteria. In the particular case that we're interested in, a particularly useful basis would be of this particular form. So it contains a parameter A as well. Okay, so this would be a basis on which you could perform expansions and compute moments and so forth. So orthogonality I will take to be defined in this particular format with respect to those canonical basis functions. I will have conventions for the three-term recurrence in this particular way. So I have usually have a it's not monic in this case. It's orthonormal. I just want to draw your attention to a few objects that will appear from time to time, and that is if you look at the large X expansion of a generic polynomial, it will have this structure with a leading coefficient gamma sub n. And the moments in this way you would define as this Riemann sum with these two basis functions, and so instead of a Hankel determinant, you would have a moment determinant with this particular structure. And you can construct a lot of the theory, virtually all of the objects in the theory, in terms of such moment matrices with bordered components, bordered rows or columns. So these will be tau functions in our integrable context. We need to look beyond the polynomials, orthogonal with respect to this weight, but to actually construct a set of associated functions, which I do in this way by defining a Stelch's or a moment generating function in this by this definition, and essentially my non-polynomial associated functions will be equal to the product of the polynomial and this function, and subtracting off the polynomial part. So these two, this also satisfies the three-term recurrence, and so you have a Casaratian relation of this particular form. The total object I'm going to be dealing with is this 2x2 matrix. So we'll be in a 2x2 system with those solutions. Okay, so the three-term recurrence will recast in this particular form with that recurrence matrix. So from the integrable point of view, this is a type of Schlesinger transformation. So, okay, let's go on. Okay, so the basic notion starts with a d-semi-classical weight. So Okay, so this is a weight where the divided difference operator is related to, of the weight is related to the mean operator of the weight by a rational function. Okay, so, or you can express it in this discretized form in this way, where the W and V are important spectral data functions. Okay, so they are polynomials in X of low degree. So, given that characterization of the weight, what does it mean for the orthogonal polynomial system as a whole? Well, first off, it means the Stieltjes function satisfies an inhomogeneous form of the linear equation I showed you earlier. And the inhomogeneous part again is a polynomial in X. And the important cases I'm going to look at, these what I would call an analog of the regular or the generic case, is where there is a strict inequality in the degrees of these polynomials. So where this is m, m-1, and m-2. Okay, so that's one partial characterization of the notion of regularity in this instance. Okay, now we want to continue this process and characterize the polynomials and associated functions using this characterization. Okay, so I define three spectral coefficients here, the Wn, the theta, and the omega n, by their right-hand sides. Okay, here. So the right-hand sides are polynomials or associated functions evaluating at an advanced or retarded node, and they're bilinear. They're constructed in this way. I've plucked this out of the air, but there is some reasoning behind this structure. It turns out, well, I mean, you know, this is a polynomial, but it's a polynomial of x, of y plus, right? It's not a polynomial of x. This is not even a polynomial. But it turns out that for this class of weights, the totality of the right-hand sides are polynomials in x only. And they're polynomials of fixed degree. In other words, the degree is independent of n, the recurrence index. Okay? So that's a very critical observation. Now, how you work out what these degrees are, that from the large X expansions of the polynomials and also their associated functions, you can actually construct large X expansions of these spectral coefficients I've just defined earlier, and they have this descending form. So, in fact, the degrees are fixed by the spectral data. So the degree of this is fixed by the spectral data of W and V and so forth, as are all the others. And again, in the regular case, you get this strict inequality in the degrees of the spectral coefficients. That's quite important. Okay. So this is why I was constructing those functions in the particular way I did, because you can turn the whole thing around and then determine in one fell swoop what the action of the divided difference operator on our y sub n is in terms of the mean of that. And it turns out, by using the Kazaratian relationship, you can easily unfold all of this stuff. And it turns out that the matrix, which prefactors here, the A matrix, the spectral matrix, is populated with elements according to the particular coefficients I defined earlier. Now you notice one thing here is that the denominator is a polynomial in X, but it's n dependent. This is quite different from the situation in the continuous case, where you would think of the zeros of this as defining the singularities, and they're not independent, they're fixed by the weight. So there's some differences emerging already here. Okay, so there are two structures here at the moment, a spectral structure and a recurrent structure. And this equation expresses the compatibility between those two. So what you find is that there's this kind of Cayley transform of the spectral matrix, and this will turn up from time to time quite considerably. You can express this matrix compatibility relation in terms of the coefficients I introduced earlier, and you get a set of 3 recurrences, which were originally found by Magnus. And so you see that there truly is a recurrence in the denominator here, which is uncharacteristic of the, which is the new feature in the discrete case. Okay, so they're quite useful objects in their own right for what's going to follow. There is something also somewhat more important than those. There is a bilinear equation. It can be viewed as a recurrence in this object, but it's a determinantal relation. It's a relation that involves the determinant of the spectral matrix. And it relates the objects that I had set out earlier amongst themselves in this particular way. Okay? So this is a scalar quantity, but it's a polynomial in the spectral variable x. Okay? And it contains a lot of content. So in my trivial example with the Askey-Wilson system, I'm going to be able to derive virtually, well, a lot of facts about the Askey-Wilson system just from that relation alone. Okay? So that's to give you some warning. There is a determinant evaluation of this particular Cayley transform, which is very nice, and its inverse is also simply constructible. Okay. All right. So here's the this full matrix product that appeared earlier, and again re-expressed in terms of combinations of my spectral coefficients. So it motivates a new bunch of kind of definitions that you see there. So this particular object is going to assume significance. So, okay, here's the example, right? All of what I've said before. We've done some general theoretical setup, so now we can kind of put it to some use, right? Okay, so let's see how this goes. So let's start with the Askey-Wilson weight. Okay, theta is that phase angle in relation to z is e to the I theta. In this case, I have 4 parameters here. That's a standard object. The first thing you do, so I'm going to be very explicit and algorithmic. So first thing you do is you compute what these 2 polynomials are. Okay, the delta y, I told you what that was some slides back. So it's a matter of you do a computation and you find out that it has this product form, this neat product form. And when you strip away these 2 particular polynomials, then you find that I get a 2nd degree one for here, a 1st degree one for here. Okay, so that's the minimal trivial seed case, if you like. Okay. Okay, so you have that data, and then what you do, you simply parameterize the spectral coefficients I have with unknown coefficients. You know their degrees, so the degree of this guy, I should have hidden this from you. I should have done this progressively. This is quadratic. This guy is linear, and this guy has degree 0. The leading coefficients are given by the expansions, and then you simply use that determinantal relation to set up a system of quadratic algebraic equations, standard problem in algebraic geometry. But you don't need to use Grosvenor bases or anything sophisticated. You can solve it in a very simple-minded way, and you can solve it explicitly. So you can find out precisely what the coefficients are of all of these just from that single relation. You can also pull out what the 3-term recurrence is, because in particular this a squared, because this is also appearing in that bilinear relation. It's something you could do by hand. You can determine what the diagonal part of the Jacobi matrix is from the recurrence compatibility relations. So you've already determined a heck of a lot. You know, you can already work out what the Askey-Wilson integral is. You can work out a whole heap of things, you know, by implication. Okay, so this is just solving a polynomial equation. starting with the weight. Okay. Now, just as an aside, I think these deserve the name of structural equations because they relate the polynomial associated system with the same parameter sets. So that spectral equation is an equation, divided difference equation for y with the same parameter sets. Yeah. Yeah, sure.
In the equation where you're saying an squared is equal to what have you,
Yep.
is that some sort of recurrence for a, or?
No, it's explicit. Sorry, a sub j here is the parameters and the weight. I'm sorry.
Okay,
A sub n is the upper.
I'll assume one of them's rect. That's discrete.
Yeah. Right. Okay. And the sigmas here are the elementary symmetric functions of the A1, A2, A3, A4. Okay. So, all right. Actually, Magnus also worked out the basic hypergeometric forms of the polynomials through this through essentially a very similar approach as well. So you can essentially get everything. This is my base case. Okay. So whatever I do from here, I extend this. Okay, so I'm going to think now, okay, I've taken the simplest case, this base case. Now I do something to the weight. So this is my deformation, not Q deform it. Everything's Q already. I deform it, so I introduce another lattice with another variable, the deformation variable. But I basically say that, well, I've got to have a similar structure here applying to the divided difference of the weight in relation to the mean weight. I get some other polynomial factors in R and S. Again, they're polynomial in X, but that's all I impose. So that's a parallel structure. There is a consistency that must apply, and it's given in this particular form. Okay, so you can even mix lattices. There's no the spectral lattice and the deformation lattice don't have to be the same. And again, a consequence of that for the system as a whole is that there is an inhomogeneous equation, again, operating with respect to the deformation variable u, and again, you can establish that this is a polynomial of fixed degree in X only. And again, there's a compatibility between my earlier inhomogeneous equation, which involved u, and this new one, which involves t. So if all of those are satisfied, then you can go. Now, there are parallels with everything I've told you before in the deformation setting, okay? So with a bit of guidance, you can construct bilinear quantities of the polynomials and associated functions at the advanced and retarded points on the lattice. And I've given you 3 here. There are actually a couple of others, but they're related by a simple relation back to these 3. Okay? And again, when you think about it, okay, so this is a polynomial in X, but this is certainly not. And but it turns out that the entire combinations on the right-hand side can be shown to be polynomials in X only of fixed degree. So, okay, and then you want to look at the leading order expansions. This, in a technical way, is how you introduce the variable n, the recurrence index, into the system. So they have this kind of particular structure, and there's a and you can see the degrees of these objects appearing as fixing what the degrees of the deformation coefficients are, and so forth. Okay, right. And again, you can do exactly the same thing. You can invert those definitions and express it in terms of a divided difference in the deformation variable of this is linearly related to the mean of that via this matrix. And the particular elements are given here. Now, there's only really 2 generally independent elements. There are simple relations between the off-diagonal ones and also a trace relation on the diagonal as well. So there's parallel structures all the way through. Okay, so we've got three structures, so let's think about the compatibility between the deformation and the recurrence structure. Well, again, you find this Cayley type transform appearing here, and this recurrence structure. It turns out that expressed in terms of the deformation coefficients, things get slightly more complicated, but you can write down recurrence relations in the deformation coefficients in this particular way. Okay, so let's push on. There's also a determinant or bilinear equation as well. So it takes this particular form. So this is the determinant of B essentially here. And so that allows me to find explicitly determine the determinant and the inverse of that Cayley transform. Okay, we're almost here. Okay, and again, this is just kind of expressing this Cayley transform in terms of the original deformation coefficients, and again, it motivates these new kind of definitions. So parallels are very compelling between the two structures. Okay, so the last compatibility between these three is the spectral and the deformation compatibility. And again, it takes this product form. So you have essentially a Cayley transform at an advanced deformation node times the Cayley transform of B at a retarded spectral coordinate, and then you have the reverse order and the reverse retarded advanced situation. Okay, I promise you something explicit here. Okay, so people have probably alluded to this a little bit in the past, so in this meeting so far. That is, what do you do with all this stuff? How can you actually use it in an algorithm sense to derive things explicitly? I'm a very practical person. I want to derive recurrences, okay? Characterizing things. Okay, so there's three basic steps. The first thing is to parameterize the spectral coefficients in a minimal way, okay? Use all your constraints, such as that bilinear equation, to essentially reduce the number of unknowns to as small an amount as possible, okay? Now we've got a B matrix, and we don't know how to construct a lot of that, so we want to be able to close the system. We want to be able to relate the deformation, the elements in that deformation matrix back to the spectral matrix, okay? We want to be able to close the system, okay, as much as possible, so we want to do that. And the third task is to derive dynamical equations for some coordinates. Now we have to work out what coordinates we're going to use here, and that's part of the that's an important part. That's the art form of this. Well, I'm treating it as an art form. I'm sure there's a scientific way of doing this, and so you want your final task is to find evolution equations or dynamical equations. So what we have to do is we have to take the compatibility relations and either resolve them in some basis, okay, just expand it all out, or we look at residues in some sense. So this is where the analog of singularities occur, but they're not singularities in any sense. But you find that there is a quantity whose zeros by which you resolve these compatibility relations, okay? It's not the zero of the denominator that you saw in the spectral matrix, the Wn. It can't be. It's the zeros of this quantity. It's the zeros of w squared minus delta y squared times v squared. That's a polynomial in the spectral variable, and one is interested in looking at particular zeros of that, okay? And evaluating them both at advanced and retarded positions. And that allows you, okay, so, right, so here comes some more explicit stuff. Okay. You have the undeformed weight, Askey-Wilson weight. Now you've got some choices here, okay? Okay, now I'm giving you one choice here, right? But there are actually lots of choices, okay? You just have to be consistent as via the consistency relations I have there. Now, I've jazzed up the Askey-Wilson weight in this particular way. So I'll just explain. Okay, what was 2 has become a 3 here. What was 1 is 3 on 2. What was just theta is 3 on 2 theta. And instead of 4 cube products here, I've got 6. Okay, so why have I done this? This happens to be in a family of weights that was studied by Ismail et al. And they made an interesting observation which related the a Sturm-Liouville equation, the Askey-Wilson operator, to the beta-Ansatz equations for the XXZ model. Okay, and this was the weight. This is one of that family of weights. So that's my interest here. Okay, you can deform it in other ways. Okay, there are kind of deformations you can occur that are gauge equivalent, and there's some that aren't. Okay, so okay, all right. So what I'm doing here is my deformation is done so that my weight is symmetrical under t goes to t inverse. So in actual fact, everything is a function of u. This. So I'm selecting my deformation lattice is a quadratic lattice. So I've got a quadratic spectral lattice, a quadratic deformation lattice. Sorry, Q quadratic. The sigma tilde j's here are the elementary symmetric functions of all of the parameters here. Okay, so let's just think about the counting. We've got the 4 basic Askey-Wilson. We've got alpha, which is the deformation parameter, and u, which is a deformation variable. When I deform, I've always got to have 2, a deformation variable and a deformation parameter. Okay, so I need that. So that's 5. The sixth parameter is n, the recurrence index. And how the recurrence enters into this is by a construction that treats it rather differently from the other parameters. Okay. So those large X expansions that I gave you, which did fix the leading terms of these spectral coefficients, that's where n enters. Can't enter it any other way. Okay, so that's where we could put it. Now I define some quantum numbers here. So for integer and half integer cases, I will find that there are 2 objects that keep reoccurring throughout the entire analysis. Okay, so we start with the algorithm. We've got our weight. We find what the spectral data is. In this particular case, this quantity happens to be a nice product form. Okay, and when we look at the polynomial parts of this, the w and the v, then what we find is the situation is that this is cubic and this is quadratic, and that's what we need. To go beyond basic Askey-Wilson, I need to raise the degrees by 1. I need to push all the degrees up. So I've done that here. Okay, now what I'm going to do to parameterize the spectral matrix is simply to use that bilinear equation again. Okay, it's a bit bigger now. I have more undetermined coefficients, and so I'm going to have extra equations. That's fine. The whole procedure goes through. Okay. Right, so just I want to note here, okay, so the degrees are here 3, 2, and 1. Okay? And this 1's important. It means that this has a simple 0. And the 0 of this guy acts as my transcendent, my analog of the plane of A transcendent. That's always going to be the case. So that's a good coordinate. Okay? Right, so I've called that lambda sub n. Now, what's also going to be useful in what you see below is that I'm going to look at the evaluation of the sum of the diagonal elements of the spectral matrix at this transcendent. It's going to be one other variable that's going to turn out to be important, and the difference. So the nu and the mu, they're not independent though. they're related in this way. So where does this come from? Well, that is just a writing of the determinantal relation evaluated where the spectral variable takes the value of the transcendent. So that's all that expresses here, okay? So there is this interesting conic type of equation emerging here. Okay, so then after a little bit of work, you can actually parameterize this matrix in terms of those three, okay? So you find that this particular quantity can be given as a cubic here in this form. This particular coefficient has a quadratic form of this one, of this type, and this is the linear one that we've already discussed. So that's a first achievement. It will turn out that in fact some coordinates are going to be more suited in certain applications than others, but that's an important starting point. Okay, right. So let's go back to our system. So what are the recurrence coefficients? The a sub n squared and the b of n. So yeah, I'm slightly redefining some alternative variables. So this is the coefficient of degree 2 in spectral coefficient, and this is the one of degree 0. I can fairly simply write the three-term recurrences in terms of those, okay? The three-term recurrence coefficients aren't usually, invariably are never useful coordinates, but they can be simply expressed in terms of the other coordinates. So this is a fairly explicit expression in terms of my basic variables. Okay, so one can go a little bit further and look at the recurrence relations. So we want recurrences in n. We want recurrences that fix n. Sorry, that fix the entire system in this recurrence way. So I'm going to give you them in two parts. This is the simple part, if you like. So there's a simple recurrence on this particular object and this object. Okay. So this is given back in terms of the lambdas here and so forth. Now, to complete the recurrence system, I have to find out what the a sub n plus 1 square of it is in terms of the original system. That's starting to get a bit more complicated, but and again, I just want to point out that it's a quadratic function of my original variables. So it's quadratic there and essentially linear elsewhere. Now now we've got to use this in the next slide for lambda sub n, and that's a bit worse. But again, it has. So this is this again. So on the left-hand side, so you have the lambda n plus 1 here. And the previous quantity I discussed. And again, it's a quadratic expression in terms of all the remaining variables. So this constitutes a recurrence system, which is the simplest one that I can see. This is a translation in the system that's not necessarily a particularly simple translation, translation on the lattice. So what you invariably find is that if you go to other orthogonal systems, such as biorthogonal systems on the unit circle, the recurrences that go there are clearly more canonical Pain-Levé type recurrences than you find with this orthogonal polynomial systems on the line. There's a big difference between the two n recurrences in both cases. So even if you did this for Pain-Levé 6, you'd end up with particularly messy things. Okay. Now, I want to head towards the evolution system now, okay? So what I'm going to do is I'm going to drop all reference to the recurrence, index n. So lambda I'm going to strip away. Okay, so I'm going to invert lambda in terms of a new variable L. I'm also going to create two new variables to replace my mu and my nu. So this is the z plus minus. Okay. So the reason why I'm constructing this particular combination is because the product of these two, z plus z minus, is expressible simply in terms of L. Okay. So what I'm doing is I'm rewriting everything instead of x and u, now in terms of z and t, and also in terms of L. So the elements of the spectral matrix then take very nice product forms of this character. So here's the upper right diagonal, and here's the upper right off diagonal, and this is the upper left diagonal element, and it has a nice interpolation expression in terms of well, L z plus minus. Okay. All right, and similarly for the others. Okay, so we're heading towards using the compatibility between the spectral and the deformation recurrence, the deformation structures. Okay, my R and S in this case, so these are the coefficients that arise in the deformation derivative of the weight. So these again have a product form in terms of Z and so forth. And you can check that they satisfy the consistency relation. There is a particular quantity that will arise here in the compatibility relation that leads to terms that show up in the quadratic lattices that don't appear in the linear lattices. So it will have this particular structure. So that's just a signpost for that difference occurring. Okay, we know the degrees of the deformation data, so we can fix the degrees of the deformation matrix, and they're lower than our spectral matrix. So we have degree 1 essentially in the diagonal and degree 0 in the off diagonal. Okay. Yeah. Okay. So we're almost there. Okay, so this is the first thing we do. So the spectral and deformation compatibility is a matrix equation. You can just put all your parameterized forms in, and its elements are big Laurent polynomials in Z. Okay? And you just resolve it as Laurent polynomials and look at the leading orders. The highest one, which occurs in the 1, 2 case at degree 7, and then you can start reading off some relations which close the system. So these are relations that start to close the system. So these are two important relations which relate the off diagonal to the diagonal elements of the deformation matrix. So you need that. This kind of procedure occurs in whatever system you're doing. So you can apply these ideas. So this is certainly, you'll find analogists, or in the Jimbo and Sakai work, they don't have any proof, but if you work through it and you attempt to derive the evolution equations in that system, then this type, you can just use these steps as well. Okay. Okay, so the last part is you can't continue doing this resolving process to get other data. You have to choose another approach. Again, I mentioned that you're looking at the zeros of a particular function, the w squared minus delta y squared v squared, which is straightforward polynomial in terms of x and the parameters and the variables. So this is an essentially a reduction of those parts of that matrix equation at those zeros. Okay, and when you actually okay, so I've given you two examples here. So they're evaluations where the deformation coordinate is advanced. Okay, And when they're advanced, you find there's a particular 0 at alpha t, and there's a particular 0 at this value. And the equations, those compatibility relations, so these are a couple of them here in this particular case, and 2 of them here. Just as a matter of interest, so this is an additional term which occurs in the quadratic lattices that doesn't occur in the linear lattices. So, whereas the appearance is basically similar between those 2 lattices in each of the 3 cases, the other 3 cases here. Okay, so we're basically setting up a bunch of overdetermined linear systems and trying to go through an efficient procedure to extract error. Okay, so at the retarded coordinates, then you have something analogous. So you have these relations, and you'll recall that these particular functions are, you know, higher order kind of Laurent polynomials in the spectral variable and so forth. So, and again, you have 3 simple ones and 1 which has these additional terms. Okay, so what's the procedure? You just start to eliminate with these in the sense of trying to knock terms out of the right-hand side in here and reduce them. Okay, so you want to have basically the essence is to find a 2 relations for the same quantity. Okay, and then compare them. So I won't drag you through that those details. Okay, so I'll just go to the result. Or one of the results here. Okay. Okay. So what you've got to do is find some new coordinate transformation here to reduce the number of variables. I've been working with 3 so far, but there's really only 2. Okay. So the first step is just define this polynomial. Then I'm going to. I told you earlier that the product of these 2 is expressible as a product of L's and so forth, and I somehow have to split that relation. So I decided to split it in this way. Okay, so I split it by taking off part of that product and defining a variable z, and the remainder simply goes with the other variable. I will then need to make a further transformation from z to f in this particular way. So I'm pulling this out of the hat. It comes out from the elimination analysis and exhibits itself to you. So in essence, you can read this off whichever system you're working with, whether it be the little Q Jacobi or whether it be the Askey-Wilson. Okay, you do that so that you can get a simple recurrence, and the recurrence is this. So this is one of the recurrences. So here, what I do is my advanced f is f hat, and my retarded f is f check, and the same with L. So one of the pair of the T evolution equations is this. It expresses the advanced f as a linear fractional transformation of the retarded f, and the coefficients all depend on the retarded L. And the retarded L, these other coefficients are fairly simple polynomials in L, and I've exhibited 3 of them rather than all of them. Okay, now that's not exactly one of the canonical Q-Pavlov systems. So I'm not going to tell you an answer whether it is this one or that one or whichever one is. I have my suspicions about it, but I can't prove that at this point. It is right. It arises from the compatibility of a lax system. also, okay, perhaps I should rewind. So in the linear cases, you have the Birkhoff and Carmichael theory for the solutions of the kind of linear difference systems or linear Q-plane systems. There is no equivalent theory for the quadratic lattice or the Q-quadratic lattice. So I'm going to, and we certainly know that from the work by Jim and Sakai that what's preserved here in their system is a connection matrix. So it's a connection matrix which relates fundamental solutions about the fixed points of the lattice. So in the Q linear system, the fixed points are at 0 canonically and infinity. Okay, so that's where delta y vanishes, or is or delta y over x goes to 0. In this particular case, there are fixed points, and so what I'm conjecturing is that if one had an adequate theory to account for this, then what I think would happen is that you would have a connection matrix which relates the fundamental solutions at these two particular points in this way. We certainly know it's a d-constant function with respect to x. So from the monodromy analog point of view, it would be the analog of a constant matrix, and it's certainly preserved with respect to with the deformation variable. So that's what the lax structures imply to you here. So okay. So what I'd like to do is just end with some conclusions, partly motivating more work in this area, and of course we're going to hear more about that tomorrow as well, and to also motivate interest in working on the appropriate generalization of the Birkhoff and Carmichael theory for these other lattices, which are quite different from the linear lattices. And yeah, so I'll leave it there. Thank you. Don't be shy. Yes.
Because is it possible to get the elliptic panelet also out of the Askey?
No, well, as Eric remarked to me, the way to go there. Okay, so these particular okay, so you've got to go from polynomial systems to biorthogonal rational systems, and by doing that, one can go from the lattices which are characterized by a quadratic relation to a biquadratic relation, and then you can get the elliptic lattices. So the quadratic lattices that I've discussed here are parametrized by the elementary functions, but if you go to this biquadratic defining equation, then it's parametrized by the elliptic functions as Rodney Baxter has worked out and so forth, and then yes, I believe you can just lift the stuff and kind of generalize it in that direction. So I didn't want to get into elliptic territory, but that seems to be the trajectory that one could go. I also remark that for a lot of the ASCII table, one can find an biorthogonal rational system and the weights. So what one could do is treat them in this way. So, for instance, the Bjarne work takes the Pastro weight, which is a direct analog of the little q Jacobi, and treats that. And of course, in a biorthogonal system, he gets a nice clean n recurrence, which is a canonical recurrence. But he didn't treat the system consistently, in my view. He patched two different methods together to arrive at the result. But there are certainly analogues of these other weights on the unit circle with biorthogonality. Yeah, and But because of the application and because the ASCII table was set up this way. So I have my view of how the table would be restructured according to this thinking, okay? Yeah. So there are many kind of representations of. There are many isomonodromic, quasi-isomonodromic interpretations and kind of realizations. It's not unique.
Thanks.
Thanks.